Okay, so I'll be talking about developing of sensors for antibiotics and resistant bacteria. And for that matter, we honed in on an optical fiber-based sensing platform based on our experiences in the past of developing sensors. And we'll talk about that. So, but since I always forget at the end, I'll start off with the acknowledgement. Of course, the funding for all of this work is provided by various government agencies, DBT, MIT, DST, NIL, and so on. A whole bunch of students have worked on it at various points of time, and the students' names mentioned here have actively worked on components of what I'm going to present today. And of course, my colleagues, Professor Tapan Kundu, Professor Suparnam Mukherjee, and many others. And IIT Bombay has nice analytical instrumentation facilities, which we use frequently for analyzing analysis and characterization. So the question is, why develop sensors at all? Particularly when we are talking about the industrial use. We need to monitor and control processes. And if we need to monitor the processes, then the monitoring methods cannot be too expensive. The systems which we use for detecting antibiotics in a waste stream or in various parts of the plant now are either the sensitivity is low, or if the sensitivity is high, the cost is extremely high. And not only the cost is high, the instruments used, typically the mass spectroscopy instruments, they are lab based and cannot be used at the point of sample collection. And so it has to go to the lab, to the sample, sample preparation, then run it, and then the result gets back if you're lucky in a day, and so on. So when the governments are coming out with regulatory efforts regarding release of antibiotics, trace antibiotics, antibiotic byproducts, whatever, into the environment, all the regulatory efforts will be fruitless if the manufacturers are not empowered with easy to use and inexpensive methods for monitoring processes and outcomes. So that is the fundamental as to, I almost say we need to democratize the sensing process in a sense that so everyone should be able to sense the necessary parameters at a reasonably low price points. So now, what are the possible sensor platforms? One is, of course, electrochemical, which has been in use for a very long time. People have been using potentiostats and looked at CVs. The chemists are very familiar with those things, looked at CVs and done various sorts of things on the electrochemical platform. There is, of course, very sensitive platforms like quartz crystal microbalance. Again, it cannot be really taken out of the lab. Although some of the electrochemical systems one can take it out of the lab. Surface acoustic wave based sensors are being developed by various people. And under optical, there are a whole bunch of these. The typical spectroscopy, the UV-based NIR spectroscopy, again, a big instrument in the lab sort of thing. Raman spectroscopy, now some of the portable handheld Ramans are coming, but very, very expensive tools. Fluorescence based, there are SPR techniques. Again, SPR is another very expensive tool. Colorimetry, which is the cheapest, easiest, and so on and so forth, paper strip based colorimetry, which, but the sensitivity is not that high. The optical platforms are as such are very versatile and involves the optical platform that we honed in on are very versatile and involves minimum steps of sensor fabrication and use in the hand of the user. So let us start talking about the optical sensing methods. Most of the times, what happens is our UV-based typical UV-based spectroscopy, you put a cuvette of a sample in, light goes in, light comes out, you measure it using some sort of detector. But if there is any other things in the sample, if the sample is not very clean, there is scattering and other effects, which gives rise to loss in the sample. So the analyte which you are targeting might not might be overrepresented in a sense due to scattering by interfering species. And of course, there is autofluorescence. Again, it suffers from the same problem. One of the very nice techniques is using what is called evanescent wave absorbance. And for the non-physics persons here and who are not familiar with what evanescent wave is, all of us are reasonably familiar with optical fibers today. They bring all our data signals right to our doorstep. Optical fibers have the property that, of course, they can move light through them with minimal loss. Now, when the light in our high schools, we studied that okay, light goes through an optical fiber by total internal reflection, which is shown in this cartoon here, where light is getting reflected and light is passing through the fiber. But that is not something which actually does not happen. If we go a little bit deeper into it and try to solve Maxwell's equations, and but in that, I mean, if you is my cursor or visible? So in the bottom of in the bottom side of this green bar, I mean, this green bar is the optical fiber, let's say. And the bottom side, you are seeing this wave, which is a representation of the light wave that is passing through it. It is abruptly ending at this boundary, and that is something which does not really happen. What happens really is what we see on the top. The sum of the power from inside the wave actually leaks into the surrounding, and that is called the evanescent wave. And how much of the power leaks into the environment around the fiber, it depends on what is there in that environment around the fiber and how far this power goes. The power theoretically it goes to infinity, but practically about between a tenth to a third of the wavelength. So it measures things which are very, very close to the surface. Remember, the wavelength of the light that we are passing through might be around, let's say, 500 nanometers or something like that. So if I consider a tenth of the wavelength, so whatever is happening within 50 nanometers from the surface of the fiber is what affects the light that goes through it. That means all the interfering species, if I keep them away from that 50 nanometer space, then they do not interfere in my readings at all. That is a huge advantage. So that is what we are going to talk about. We are not going to talk about resonant mirror grating couplers and all those things, but we will talk about using gold nanoparticles on top of this fiber to increase the sensitivity and tune a few things. So another picture of this evanescent wave thing. As you move away from the surface of the fiber, the intensity of the evanescent wave decreases in an exponential fashion for the matter. Now, in an optical biosensor, what we would like to do in the type that we want to do, optical fiber biosensor, we will have a capture molecule which is immobilized on the surface of the fiber. The analyte comes and binds to it, and preferably it gets detected immediately on binding, which will be a label-free assay. And of course, the specificity is given by the capture molecules. So only the targeted molecules are bound to the surface. The non-targeted molecules will remain in the sample medium, hopefully beyond the penetration depth of the evanescent wave. Of course, in order to increase the sensitivity, we can make this a labeled thing where once the analyte binds, there is another molecule which comes and binds to it, which is tagged with something bright or something. Something is quenches or something it gives out light and things like that. But we prefer not doing. A very simple schematic of such a sensing system is going to be where in an optical fiber, you typically have, if you buy one from the market, it is going to have a jacket outside it. The jacket is just for mechanical protection. Inside the jacket, there is a cladding. And inside of the cladding is a core. The core and the cladding are very important for the optical fiber propagation property. What we do is actually we remove the jacket, and very importantly, we remove part of the cladding from the surface of the core also. Excuse me. And that is what is being shown here, where the green color is actually not green, it is transparent, but the green is the core of the fiber. It has been stripped of the cladding which was around. Now, once you have that, you put it in a flow cell and shine light into it, focus light into the fiber at one end of it, where the cladding and all that is there. Take the light out on the other side and put it to a spectrometer, or you can put it to a simple the photo detector. And that is what we do. Now, we started off, of course, trying to detect E. coli. And to initially, what we saw was, of course, getting E. coli antibodies are more expensive than the human immunoglobulin, anti-human immunoglobulin pair. So we thought that we'll do first proof our these things using the HIGG pair, and the sensitivity was reasonable, 1 micrograms per mil. But now we have got picograms and all that. Let's not. I mean, this is quite old. This data. But what we learned from here was that although we could detect the proteins, we could not detect E. coli using this. Now, well, why? And we looked at it under the microscope and saw that E. coli cells are indeed being captured by the antibodies on the surface of the core, but the detection was just not happening. What we realized was that the penetration depth of the evanescent field is like, we were using 280 nanometer light or UV light through this. The effective penetration was about 28-30 nanometers. The E. coli cells are a micron in diameter. Actually nothing was getting picked up. So we somehow have to increase the depth of penetration of the system. I mean, as we are trying to show this in the form of a cartoon over here. In a straight probe, you barely get any interaction of the evanescent field with the E. coli. But if you bend the fiber into a U shape, what happens is at that U bend, the lower order modes of light that is passing through convert to higher order modes of light. Penetration depth effectively increases significantly, 3 to 4 times, or even more than that sometimes. So we decided to bend the fiber. Now, how do you bend the fiber? We just used a simple candle. Held the fiber on top of it, gave it a little bit of pressure, it bent to a U shape. There was quite a bit of optimization done, many types of bending diameters and all that thing. Now, with the fiber that we use, with the core diameter of 200 microns that we use, our optimal bending diameter came to be about 1.5 millimeters. So we now have a bent probe through which we can pass light and hopefully detect E. coli. This is a picture of how it is being, how the bending is done. And once we did the initial bending, immediately we started seeing about 1000 CFU per mil without any problems. And with some degree of modification, we could go down to 20 CFU per mil. And even more shocking or surprising that a sensor of this nature, which you can literally make in your garage, we could even detect 1 bacteria per mil over a 5 ml volume. But we know the 1 bacteria per mil gives a little bit of variability, as you can see in the bottom right over here. So we don't claim 1 bacteria per mil, we say we can detect down to 10 bacteria per mil. And this is using a sensing system and a fiber which is inexpensive and easy to make and use, and without any major sample processing steps involved. But there's a problem. The problem is that the 280 nanometers is UV. The UV sources are more expensive. The fiber becomes specific. We have to buy what is called solarization resistant fibers. The source is specific and the cost goes high. And the company was literally, they jacked up the price from $30 a piece to $150 a piece over a period of 3 years or 4 years, something like that. The detectors are also fewer. Photo detectors that can pick up that heat. So we wanted to look for some other alternatives, and so there we started exploiting what is called localized surface plasmon resonance, which happens around noble metal nanoparticles, gold and silver. Gold is of course preferred because it does not suffer from degradation like other metals. And what happens is that the light is absorbed. Let's see whether I have that picture. So if you have a gold nanoparticle and light comes in, there is electrons which are on the surface of those nanoparticles are set in motion in what is called a plasmon resonance at a particular wavelength of light. So on the output side, you won't see that light. That light has gotten absorbed by these by electrons which have gotten into motion. But these are localized around the nanoparticles, so that is why it is called localized surface plasmon resonance. It uh, which color gets absorbed, how much it gets absorbed, it depends, number one, on the size of the gold nanoparticle, and number two, on the refractive index of the micro or even nano environment. So if I have a purely a gold nanoparticle, and gold nanoparticles are made mostly by your method called Klutkiewicz's method, which has a citrate capping for keeping them apart. Uh, if we have just pure gold nanoparticles, and we pass a white light through it, it might absorb, let's say, 540 nanometers. But the moment we attach a layer of antibodies on the surface of the gold nanoparticles, the absorbance pattern starts changing. And then when the antigen comes and binds to these gold nanoparticles, it changes even further. So that is what we see. That is what we want to exploit. So this worked pretty well. We obviously initially we did the same thing. We used it for HIGG complex, and then we started using it for E. coli. The sensitivity was slightly lower. We actually went down to about 20 CFU per mil, but that's okay. And if you want to know how difficult it is to make these sensors, once about 5, 6, 7 years back, uh, my daughter, who was in high school then, wanted to do something in the lab. So she came, learned how to make these sensors, did some experiments, and went. Did a whole thing in 3 days flat. So one can be trained to make these sensors and do that very, very easily. Uh, Now, let's say let's try to enhance the sensitivity sample. So what we thought that, the full E. coli cell interacting with the probe, they might be sitting this way, that way, and they're captured by the antibody. So let us bring the whole E. coli cell surface as far as possible close to the surface of the sensor. But how do we do that? We cannot. So what we started doing was we tried to lyse the E. coli cell so that the surface proteins of that come closer to the surface and those are detected. And as expected, our sensitivity was indeed much higher with the lysate than with the whole cell. Now, if that happens, we should also be able to immobilize the bacteria on the surface of the probe and then subject them to antibiotics which will lyse them. And the response should change. And that is what happened. We exploited that. We put, this was not done in water, but we put some bacteria in artificial urine. We knew they are susceptible, which antibiotics that they were susceptible to, and we could get a curve, something of this nature, when the bacteriolysis was happening. But when the bacteriolysis happens on the surface, obviously the particles move away from the surface. Earlier, we were lysing before subjecting it to the before putting it into the probe. Now we are putting the bacteria on the probe already. The bacteria is immobilized on the probe, and we are applying the antibiotics. The bacteria lyses, the internals of the bacteria are literally washed away, and what we see is that the absorbance suffers a reasonably steep fall. And we saw that we do that with Pseudomonas aeruginosa and E. coli. So we could actually detect, and mind you, this is the time taken is about a couple of hours. Whereas a typical susceptibility curve distribution test, it's going to take about 24 hours. So this is a fast method of testing for bacterial susceptibility. or on the other side resistance to various antibiotics. We to this event sensor we have made a whole many different types of modification. We have done derimer coatings, which takes our things down to protein fencing in the order of picomolars and so on. But another thing struck us that if people are familiar with the chemistry, uh, polyaniline is a very well-known conducting polymer, and people have used it extensively and in electrochemical setups to look at pH changes because the conductivity depends on the pH. Uh, People have also used polyaniline on optical fiber tips to detect a pH change in the environment. But can we use it for something else? Essentially, what the polyaniline exists in four oxidation states: leucoemeraldine, emeraldine salt, and pernigranate. And the protonation or deprotonation of a polyaniline substrate changes the geometry of the polymer backbone, and it affects both the electrical and optical properties. Now, that protonation deprotonation happening uh, by the by a pH change is easy to understand. But the immune reaction happening on the surface of the polyaniline, we discovered that if a antigen if an antibody is stuck to the surface of polyaniline and an antigen comes and attaches to it, that also indirectly changes the protonation of the polyaniline, thereby changing the electrical and the optical properties. And what we saw is detection of the optical properties, very minute change of the optical properties was entirely possible using our bench probe. So what we did was we took a bench probe and coated that with polyaniline by simply dipping it in a aniline monomer solution and adding ammonium persulfate. And we optimized it to how long we need to keep it dipped and so on. And what we could see is we could very easily detect down to around 60 odd E. coli cells per mil. Now, this gives us a lot of opportunities into branching in other fronts because now we can, even with the 60 to 80, we can reduce that by looking at some other methodologies which will involve the pH changes due to the E. coli being on the surface. And we did some non-specificity tests and all that, which worked out very nicely. We could also detect. I mean, so this was the and E. coli is a large entity. Uh, our HIGG or our immunoglobulins are pretty large molecules. They have a charge cloud around it. Maybe because of the charge cloud changes, this protonation is happening. But we saw that if I put albumin on the surface of the polyaniline, albumin gets denatured by lead ions. That can also be picked up, and that we could pick up down to 1 picomolar level of lead. Now, to the exclusion of other substances, always we do interference study. We took the same thing and we looked at the hydrolysis of the beta-lactam antibiotics. We immobilized beta-lactamase on polyaniline. If the beta-lactam antibiotics come in, they get hydrolyzed. The local pH changes and we can measure that. And we could measure that down to about 10⁻² nanograms per ml, which is 10 picograms per ml. This is a sort of version 1 instrument design that we made for doing this. And this is version 2, which we actually started working. But as you can, if you look at it carefully, right over here, you can see a little green thingy like a U, and that is the sensor. The rest of it is all electronics. And we have a two-line display and all that. People don't like two-line display, so we had to change it. Now, can we use antibodies to these antibiotics to detect the antibiotic? So here, Tennyson and Tathagata, they started targeting this anti-ciprofloxacin antibody on polyaniline probes. And once we do that, we see now that we can detect down to about zero 0.1 parts per billion of ciprofloxacin. And the calibration curve looks to be pretty straight. Of course, the x-axis you'll notice is in the log scale. And we can get a determination within about 1500 seconds. There is enough separation, 1500 to 2000 seconds. Well, that's a lot of seconds, I know, but still it is better than half a day. So not only we did test, these testing was done in DI water and more clear water, and we spike it with ciprofloxacin. We did the same thing with filtered lake water. We have a lake nearby and pick up some water from there. Filter it to remove the large particles and the fungus and all that, and spike it with ciprofloxacin. We could go down to 0.1 ppb. We even took the creek water, and this creek, mind you, is a creek where a lot of industrial discharge happens. We took the creek water, and there also you can see that we can detect the our down to 0.1 parts per billion, and we can detect and the calibration curve is reasonably. And we did some interference studies. This was particularly an antibody for ciprofloxacin, so it should not detect the other antibodies, and which it did not. Obviously, you can see the bar chart on the right side. It shows that it actually does not have much of a response, or even a negative response. That happens because of some other reason, but to other antibiotics like ofloxacin. So the other one the students have targeted now is again Endofloxacin. Again, with the Endofloxacin, we see a very similar sort of thing. The MRL of Endofloxacin is 100 ppb according to the European Medicine CMA, and we can detect down to 0.1 ppb. So that is, detection in the range at which the maximum residual limit is doesn't seem to be a big problem. And again, about 2000 seconds or so, you have quite a good result to distinguish between various levels of antibiotic presence. So now this is the new system that has been developed. If you see over here, I mean, of course, now the screen is better. It's a touch screen, and you can do all sorts of calibration fun stuff over there. The data is stored in an SD card. There is an on-off switch right over here. And from there, this SD card, let me remind you that the SD card is about an inch wide. So that gives you an estimate as to how long and how wide and how high this machine is. It's about 8.5, 9 inches long by about 2.5 inch wide, 2.5 inch high, like that. This is the cartridge, and let me see whether this movie plays. Yeah, so this is how it's used. This guy is putting in the fiber sensor, and there's a guide path which just takes the fiber, two ends of the fiber, and puts them so that when the cartridge is inserted into the machine, the tips of the fiber are perfectly aligned with the source and the detector. So there's again a side rail over there to which it can be put in. And then they will put a sample there. It was inserted into that little well. The sensor was inserted into a little well. The sample is put in the well. The cover, of course, has to be closed because otherwise external light is getting in. And there you can see that it is. I mean, we have taken the baseline reading, and now it will actually start. The absorbance values will start changing. So this is oh no no. So, well, this is again using the same box. This Endofloxacin was measured using this. We could the students have done up to 10 ppb. They have not gone lower because the MRL is 100 ppb. There is no point in going to 0.1 ppb when the MRL is 100 ppb or so. Can we even have sensors which are even, you know, even cheaper? And but how is the how I mean how sensitive are they going to be? So we are talking about an even cheaper sensor now than the optical fiber. Here the MRL of ciproflox is 100 micrograms per kg, that's 100 ppb. Again, I mean I don't want to go through all of this, but what happens is you can there can be an iron 3 complexation with ciprofloxacin. So ferric nitrate to monohydrate that was chosen, and by the complexation of the ciprofloxacin with this monohydrate, we could detect down to about 100 ppb. I'll show you. Yeah, this is where we are. I mean, these of course after 1 ppm, it is not very easily visible to the eye the change in color. But if you, I mean, it essentially develops a slight yellow tinge, and using a reasonable reader, which might even be a mobile phone, we can go down to 100 100 ppb or even. This is done again with ciprofloxacin, and the way and one looks at interferences. So here it does ofloxacin does react with it. So we have a detection of ciprofloxacin and ofloxacin, not the other antibiotics. It does not is not impacted by the generally the heavy metals or the other type of metals and salts which are present in water. So that is nice. So again, I mean, we took the filtered creek water and we could go down actually to 10 ppb while doing the measurement using an UV-based system. But doing it on the eye is a little bit more difficult. As you can see that, I mean, the bar graphs on the right, I mean, there is urine, there is filtered creek water, filtered lake water, and tap water. The tap water, the interferences are general. The tap water is much cleaner than everything. So it is, we find it much more sensitive in our tap waters. So the whole thing is this optoelectronics box. It can be designed that it can work for a variety of sensors. So it's a platform for use. Depending on the capture molecule on the surface of the fiber, we can detect specific bacteria. We can detect total bacterial load. We of course can detect susceptibility of bacteria. We can detect antibiotics. We can detect heavy metals. We can detect proteins in serum. For that matter, we can even detect explosives in the air. And as I said, it can be fabricated with a minimal training and infrastructure, and thus it has the potential to be a sensing system which can be used in the factories right at the point of sampling. And so we should be able to give the manufacturers a way to monitor the output and thus follow the regulatory the regulations that are being put in place almost as we speak. So thank you.
Thank you very much. It's fascinating what you can do with optical sensors, all sorts of different things. So I think there's really a chance to sort of democratize environmental monitoring. People sort of crowdsourcing environmental monitoring. Could you? Yeah, I thought maybe you should let other people start to ask questions first, but I was kind of curious to hear from you what sort of costs would be involved to actually get this.
The fixed cost is the instrument. The instrument cost is will be If I have to say that in pounds, okay, in rupees it is less than 50,000, and so you have to divide that by 100.
Yeah, so
So about 500 pounds
yeah,
for the instruments, maybe a little less than that actually. 50,000, I'm actually going high. The bill of materials is about 20,000 or something. So 500 pounds maximum for the instrument. And the sensors, depending, it actually depends on the capture molecule. So if the capture molecules are very rare antibodies or something like that, then the price obviously goes up some. Uh, but we need a very little, very little amounts of that. So maybe the sensor cost is going to be 300, up to I would say the upper limit is 300 rupees a pop. So 300 rupees is 3 pounds.
yeah. So Dolph, you have a question.
Thank you. That was really interesting, and I really appreciated that. In that sort of second project I talked about, the slurry tank project, one of the big problems we had was detecting antibiotics in very dirty water, so very murky environment with fecal material and undigested stuff, which of course is important. And of course, you know, it required use of mass spectrometry, which was very expensive, and sample preparation, which was necessarily different for different antibiotics, and in the end we weren't able to publish from that the way we wanted to. I'm just wondering about applications in sort of dirtier environments. Could you see those as being possible, or?
No, it is completely possible. As I said, our filtered creek water, what we call the filtered creek water, there's a lot of waste that goes into that, and not only that creek it has a very interesting, I mean, it brings in the tides from the sea also. So there is a water runs both way in that creek, in some sense. So and there is a lot of industry which actually discharges into that, and the creek water is quite polluted for that matter. It can be, yeah, it can be done. Maybe we have to do a filtering, but nothing more than that.
Okay. You mean basically a crude filtering, you know, just to get
crude filtering, yeah,
yeah,
exactly.
Yeah. Okay. Yeah, that's very cool. That's very interesting. Thank you.
So one thing that I think from listening to your talk, you have used such a variety of different methods. So I guess the approach you're following is to try every technology that is possible and see which one works. So rather than being focused on one particular kind of technology, you really have tried everything that can be somehow used in for optical sensing, or are there many others that I'm totally unaware of that you haven't used?
No, you see, I stay away from trying to develop instruments which are very expensive, large, and non-portable.
Yeah.
So we don't do SPR, you know, Biocor and all that. I mean, we had our own lab developed SPR machine about 15 years back. I sold the technology to a company who was supposed to bring it to the college level laboratories and all that. They finally were not so interested. So I got some money, but they didn't do anything. So that's okay. But I don't want to revise that. We are, I mean, Raman or a portable Raman with surface enhancement. That is one of the things we are exploring. We are because we have to get we have to make those surfaces. So that is something that we are exploring, but that we are exploring right now with pesticides as opposed to with the antibiotics. You will move into the antibiotics quite soon, because earlier we did not have a Raman system in the lab. Now one has come, so we will be starting to use that with that. But again, I mean, those are lab-based characterization systems. So finally, what I want to take out into the field is something which is, as I said, a reasonably inexpensive and portable or handheld, whatever we call that. We have explored electrochemistry also. we do develop some sensors for other purposes, which are based on electrical impedance spectroscopy. And so those are primarily for measurement of volatile organic compounds. And maybe also differentiating between bacteria, viruses, like that. So yes, we have a couple of maybe 2-3 platforms, but I saw in the developmental effort, I try to restrict myself to platforms which have a possibility of being very, very portable.
Would it be possible to make it a little bit cheaper by replacing some of the electronics and display and everything by connecting it to a mobile phone?
That is a thought, but I mean, we have explored that possibility. But then it did not turn out to be the. It was not reducing the cost that significant. And I mean, in this way, it is a. I mean, by the way, this instrument can go with one battery charge. It can go for almost 48 hours. Okay. So we did not see a major utility in actually because all that the mobile phone is going to do is actually take the signal and maybe graph it and plot it and things like that. Do a little bit of the computation in the mobile. Here that is being done on a microcontroller. So not much of the electronics is going to change. The most expensive part of the electronics in there is the photo detector and the LED. So that part is not going to change. So we, although in the electrical impedance spectroscopy thing, we have developed something which hooks up to a mobile phone. But then when I did a sort of survey of people as to whether you want it with a mobile phone or a standing thing, but then you a standalone thing. Most of the people said that we'll rather take a standalone, which has its own display. But it will be nice if you can save the data to a mobile phone. Yes, here you can save the data to a mobile phone. This will have a Bluetooth connectivity to a mobile phone where you can save the data with the GPS coordinates and all of
that. Yeah, thanks. Liz, do you want to try to ask the question directly?
Yeah, can you hear me?
Yes.
Oh, okay. It wasn't working yesterday. So yeah, it was a fantastic talk. Really enjoyed it. All the talks this morning were superb, and I learned lots as usual. Maybe sometimes I've forgotten it and then I relearn it, but it's always fun. So yeah, one of the things we've noticed in these dirty conditions where we're detecting drugs is they get altered. They have organic material attached, or they get methylated, or something happens to them, or of course they're partially broken down, or some bacteria will knock off some groups. And I wonder, have you experienced much of that, and have you taken account of it, or do you just think, well, we're going to look for the ones that stay intact and as directed by your probe?
Right now, it depends on the epitope on the antibiotic, which is being targeted by the antibiotic. So if that epitope has not been knocked out, we are fine. Beyond that, I don't think we can really go yet. If the antibiotic is, literally cleaved in half, then we probably will not be able to detect the other half of it.
No.
And one of the things that is important, I mean, I've been telling some people a few days back that it is not the, I mean, the antibiotics, the somewhat degraded antibiotics, and some of those degradation products are quite endocrine disruptors. So we need to actually worry about that also.
Yeah.
Yes, I would like to have a sensor which is a little bit more broader in scope. Work is going on towards that.
Yeah. So you're trying to make sort of masking designs. I mean, sometimes I've seen epitopes masked by some ligands, compounds, attachments, and they've been testing the probe. So that's one way to go, I guess. But the ones that you see more frequently happening, like organic material masking, the detection of them. Thank you.
We have a comment in the chat from Iqbal Ahmad. Very interesting biosensor talk and development by IIT Bombay. We can make use of it if available. So that is probably the question on many people's minds.
We have contacted a company.
Yeah.
We have contacted to a company in India who are going to make for us a pilot scale manufacturing, and they do some on-field test and validation also for us. And there is probably a company in US who is showing quite a bit of interest in taking this technology up. If this company in US takes it up, then they would want their area to be in US and UK. Either way, I mean, I'm hoping that within the I cannot say that I can give it tomorrow, but well, within not very distant future, these should be available for purchase.
Yeah. So are we talking about a year or?
Hopefully, yeah.
Yeah. Okay. Yeah, that's a really interesting development. Do we have any other questions or comments? Otherwise, I would like to thank Professor Mukherjee and Stetul for their talks, and everyone else for joining the workshop, and hope you all got something out of it. And yeah, all the best, and thanks for attending, and thanks for the speakers. Yeah. Okay.
Thanks, yeah.
Goodbye, everyone.